guys, so welcome back. Happy Friday. So a couple things. One, I posted some new homework problems, homework assignment 8, I believe, on yesterday, and it's on WebAssign, good to go. Also, good job, everyone. It looks like they did really well on the homework, so good job figuring all the triple integrals, spherical coordinates out by yourself. However, what we're getting into now is a little bit tricky. It's the vector calculus. This is the main part of Calc 3, and I will say it's probably a little bit more difficult to learn on your own, so hopefully these videos will help. I'm trying to dig up material on Khan Academy and things like that. I may even, like on certain homework problems, if a lot of people are having trouble with it, you can email me and I can actually type up my solution to it and you can see the solutions. So we're still in section 13.2 on line integrals. And there's actually two types of line integrals. So let me talk about just the scalar. This is just a review. But what the scalar is, what a scalar line integral is you're integrating kind of a two-dimensional. You can also do this in 3 dimensions. I didn't do any examples, but and we probably won't. But you're integrating in this two-dimensional object, this surface, over a one-dimensional object, a curve. And so the way you do this is you parameterize the curve with something, call that r of t, and then you multiply by the magnitude of the derivative of r. So this is like the arc length, and then you integrate this out. Okay, and here is a picture of what's going on. You've got some C down here. You've got your surface up here. And so what you're doing is when you plug in all the points along C into the function, you will get some type of curve up on the surface. And if you look at the area of this little sheet below the surface and above the curve only, it will be given by this formula. That's what that means. Okay, so that's scalar line integrals, and we did, I did 2 of those yesterday. I can do some more. I'd appreciate feedback from you guys. If you watch this video and you're struggling with this stuff, shoot me an email and I can make some extra videos on just some more calculations. But now what we're going to get into is vector line integrals. And so if you recall back, back in maybe the first chapter, we covered chapter 12 on the dot product. If I take a force vector, so I take just constant force vector, and I apply that to an object at, say, a position P, a point P, and Q, and I apply this force to an object here, and I make it move that object to Q. Then the work, the physical quantity of work done, is you make a vector at a PQ, and you do F dot that vector. Okay? And that's a simple thing. So, basically you can think of gravity. The work I do to lift this marker is gravity's going down, and so I have to apply an opposite force to make this go, and I can calculate that work. Okay, so this is a great idea and all, but what we're going to do is the following question. What if F is not a constant force vector? But rather, a vector field. Okay? So now, what if, here you're assuming F is like a constant here, right? And a good example of this, one way you can think of this is the gravity example, but maybe dragging a wagon, if you think about that, you're putting a force on at an angle. All right, so fine. what happens now? So here's the picture. Okay, and also, what if F's not a constant force field? And what if the P to the Q is not a straight line? Okay, so sorry to add to the question. So here's a picture of what we've got going on. Recall a vector field now is a bunch of vectors. Okay, so imagine I've got a bunch of vectors going on. And maybe they do something like this. They get smaller as I go to the origin, whatever. Okay. All right, so here's my vector field F. It's a function of two variables. And then imagine I have some object here starting at P, and I go along the curve to Q. Okay? And now I want to know this question. What is the work done moving an object along the curve C by the vector field F? Well, here's the idea. Let's just examine it maybe at a little bit of a micro level. If I chop this curve up, first off, let's parameterize the curve. So the curve's got some parameterization. Again, we're going to talk about this, but it's called R, and it's a function of X. Okay. Well, if I chop up this curve, say, into a little piece, imagine this were just a little straight line right there. Then I could approximate the work just done on this little tiny interval by looking at the force vector dotted with a vector under those two guys. And what this vector, roughly speaking, is that's going to be like my tangent vector, okay? This is going to be like the tangent vector to the curve. So just a little slice of work is going to be something like this, okay? This is going to be like, and we'll call this actually a little dw, and this is like a dt, a little slice of work. And so, turns out that's how you do the general work. In this hole and moving it from P to Q along this curve is you just dot the vector field, plug in the points along the curve into the vector field, and dot them with the derivative of your parameterization, and that's it. All right, so this may look intimidating, but it's not too bad. And so the vector, right marker here, vector line integral. And so what this is I have a vector field, and then I have a curve with parameterization RT. Okay, so this is X, T, Y, T. We're just doing two-dimensional vector fields here, but you can just as easily do two. And then the vector line integral is written like so. Okay? This is f dot dr. And so what this thing is is I take, and so my parameterization is going to range from some interval t to a. And there's some important things here that are, so some important differences here, but what I do is I plug in all of the points of my parameterization into my vector field, right? The vector field I should write up here, guys, sorry, is it's a function of two variables, and usually it's p and q. Two variables, two outputs, etc. Okay? And so what I do is I dot it with the derivative. Okay, and this is our vector line integral. And what it represents, again, it doesn't have this like nice geometric meaning of area under curve or area somehow that the vector field is carving out. This is the work done by the force. Work done by F along C. Okay? And that's its physical meaning. So this is a vectored line integral. Let's see how much time we have and see if we can just compute one of these guys. All right, so let's do one. And we'll talk about several other things. Okay. So compute this where C is the parabola x equals 4y squared, where y is ranging from 5 to 0, 2. Okay, so I didn't really go into it, and I'm going to go into it after we finish this example, but with vector line integrals, in other words, when we're doing these vector, and notice the notation here, that is a dot. We're dotting it, that's a vector dr. With vector line integrals, the orientation of the curve, in other words, which way you transverse the curve, actually plays an important role. And you can think about that in terms of this physical meaning of the work. In other words, the work, if I take and I move a particle from P to Q, if I go from Q to P, well, that's the opposite. I get negative. I will get the opposite of what I got before. So the actual orientation of the curve matters. And so when you do vector line integrals, you're going to specify from here to here. And this is not present with the scalar line integrals. The scalar line integrals have this positive meaning that they're just this area of the sheet underneath the surface. Okay, so let's draw our curve here, and let's think about how we can parameterize it. So our curve here starts at, and sorry guys, I messed this up. I did not write this in my notes. This should be a negative 5, 3. Sorry. 5, 3 was not on this curve. Okay. So negative 5, negative 3, somewhere down here. Okay. And then what happens is this parabola goes up to here, up to 0, 2. Okay. Here's our curve, and now this, and sorry, that should not be from, that should be from negative 5, 3 to 0, 2. Okay. And now this curve, a particle moving along this curve, starts here and goes here. Okay. And then we've got this vector field, and I'm not even going to try and draw this vector field, but some, it's got some arrows here. Okay. So first off, we need to parameterize it. Well, it's really easy to parameterize this x as a function of y. You let y be the independent variable, x be the dependent variable. In other words, this will do it. This will parameterize it, right? This is my x, this is my y, and my y here is going to range from -3 to 2. Or sorry, my t will range from -3 to 2. And so when t equals -3, I end up down here, and then as t gets bigger and bigger up to 2, I go up to that. Okay. And so notice for my vector line integrals, I also need to compute my derivative, which is -t squared 1. Sorry, that was not correct. -2t. There you go. All right, and then now we're ready to do this vector line integral. So this is, I drew this vector field. This is the work this vector field does in moving an object from here up to here. Okay, so what this is, what I'm going to do is, and by the way, my vector field here is, this is an f. So I'm going to plug in y equals t, x equals 4 minus t squared. Okay, notice I plugged in y equals t, I got t squared. I'm going to integrate this thing from -3 to 2. Okay, notice the -3 and 2 are the values on y because it was our independent variable. And then I'm going to dot it with this. Alright, and so what I get is, when I multiply all this out, I get -2t cubed plus, so I'm dotting these, so I multiply the first components together and the second components together, and I add the 2, plus 4 minus t squared dt. Alright, and well, about out of space here, but let me just write down at least the integral. So this is -2t to the 4th over 4 minus t cubed over 3, and then plus 4t, and I need to evaluate that at 2 and -3. And you guys just have to take my word for it. See, I'm running out of room on the computer. But I think when you evaluate, when you plug in these numbers, you can do this at home, double check. I think you get, let me just write up here. I got cut off. I think you get, at least I came up with 245 over 6. Not the nicest number, but that of course tends to happen with these things. They don't end up being the nicest numbers. All right, so that is our first vector line integral. Okay, so a little bit of an alternative point of view here. And we'll get into some of the nuts and bolts and some of the things about this, but a little bit of a different point of view. And you'll see some of the questions on the homework are written this way. And so say I have a vector field. I'll write it like this, P, Q. Okay? P and Q are exponents. Usually you kind of suppress the variables. Okay? Well, if I look at what this is, this is, I'm going to plug in R. I take whatever parameterization I have, and then I dot it with R prime of t dt. Well, this right here is P of R of t. Dotted, when I do the dot product, I get x prime of t dt. And then I have Q R of t, and then I get y prime. The x prime and the y prime are coming from this guy as a vector, okay, the vector of those two, dt. And well, when I multiply these in, x prime t dt, that's actually dx, okay? And y prime t dt is dy. And so it's really nothing but, in terms of the viewing this, a different way, an alternative way to do it is to write it like so. You write P dx plus Q dy. Okay. All right. And so this is actually the way I like to write them. And so let me go back to that previous example we did and kind of compute it with this language. So first off, here was our example. Our f was y squared x. Okay, that was our f. Well, so I can write this thing like so, but an alternative way to write it, or sorry, let me actually erase this, so I can write this like so. Okay. But an alternative way to write it is exactly the same thing. This is equal to it, is you write y squared dx. You're looking at what's going on with y is hitting the change in x, and you write x dy. And so you'll see the homework full of these kind of weird little, and so it's kind of weird, right? You've got dx and dy, but that's the way we do it, okay? And so when you're evaluating this, actually, I don't know why I boxed that in. When you're evaluating this, a little bit easier way to go about it is recall our x was 4 minus t squared, and our y was t, and our t was trapped between -3 and 2. Okay? And so when you're doing this, what you do is you go from the -3 to 2, fine. You plug in the y, this is t squared, and then the dx, well, you just do a little calculation. dx here is -2t dt. And so you get -2t dt, and dy is, so x I plug in, my x is going to go there, and then my dy here is just dt. And then usually you don't write the dt. This is where it's a little bit of abusive notation, but usually you just write the dt over here. And when you multiply this out, you get the exact same integral. And like I said, this is just a little bit different perspective. Okay, so how much time do we have? All right, guys, so that's all for today. I'm going to give these a shot. You should be able to get started and start doing most of the homework. And then I'm going to get into a little bit more of the nuts and bolts of this stuff on Monday, and you should be able to kind of finish up all of the homework by Monday. Have a good weekend. Bye.